Okay, so now we're going to talk about the naming of acid. Naming of the acid is the naming of the acid is close to the name for ionic compound. This is close to the ionic compound. But before we talk about acid, we need to recognize what kind of chemicals. If you give you the formula, what kind of chemicals is called acid? Usually, if you see there's a hydrogen in front, and then there's something in the hydrogen plus anion, then this kind of formation is called acid. So for example, HCl. Have you ever seen the HCl before? So hydrochloric acid. HF, H2CO3, carbonic acid. H2SO4, sulfuric acid. HNO3, nitric acid. Okay, so those are the acids. They all have the hydrogen for the first elements. Okay, they always has a hydrogen as the first elements over there, and then they are adding the anion over there. But if you look at those formula, you will recognize some of the anion as only just a single atom. You see, those are the single atom, but some of the anion has multiple, which is a polyatomic ion. Okay, so they have a different. Some of this only have a single atom, some has multiple atoms. Okay, so when we give it a name, they have a different name. Okay, so that's why we need to talk about. So first of all, if the anion is monoatomic ion, if the anion is a monoatomic ion, then we'll give its name. We add a hydro in front. This is only for monoatomic ion. We add a hydro in front, and then there's no space. We're going to plus the element's name. Then we plus the ending. The ending will be plus ic and acid. Okay, so the ending, we're going to have a hydro. First, we add hydro in front, and then add the element's name, then plus ic and plus acid. Okay, so ic and acid, there's some space over there. So HCl, that's why it's called a hydro. And then element's name is talk about the elements other than the hydrogen. Okay, so here this is the chlorine. So you put the chlorine over there, and then you need to get rid of some of the ending, just like what you do for the other cases. And plus ic acid. So if you combine everything together, you will find that's gonna be hydrochloric acid. Hydrochloric acid. You see, yeah, HCl, hydrochloric acid. Very, very common acid. So I hope you're gonna remember this. Okay, hydrochloric acid. Okay. The other one, like HF. HF is also a very common acid. So based on the rule, you will see hydro, and this is called the fluoride, right? This is fluorine. So this is fluorine. This is fluorine. So fluoric acid. hydrofluoric acid. You see. By the way, just mention a little bit. HF, this one is a weak acid. The weak acid and strong acid, that means the acidity is different. Okay, HF has a pretty weak acidity, but it doesn't mean it's not dangerous. HF is very dangerous. Okay, it's very corrosive. Okay, I handled the HF while I was a PhD student. Okay, we're using HF to digest the soil. So generally, soil is really hard to digest, except the HF. Okay, we can plus add the HF and some nitric acid over there, and then it will dissolve the soil very, very easily. Okay, just a little. So when we handle the HF, we need to wear a very special glove. Okay, because normal glove, HF can easily to penetrate the latex, the latex glove. Okay, and also if just one drop of the HF, okay, put on your finger, probably half an hour, you will see your bones. They can penetrate your skin, okay, very easily. And then, so that is why HF is very corrosive, okay? HF can dissolve a lot of the silicon related materials. I'm talking about silicon related, which means soil is kind of like the rocks. Most of the rocks are made by the silicon, and the glass, okay? Glass is also made by the silicon. It's a silicon dioxide. Okay, so so when we contain hold the HF, you have to using the plastic things to contain the HF. Okay, very, very corrosive one. Hydrofluoric acid. All right, so then how about this? H3N, H3N. What is this called? Based on the rule, what do you think? You put a hydro in front because this guy is a monoatomic, so you put a hydro. And then what is this called? You plus element's name, nitrogen, right? And then you get rid of the ending, and you put ic and acid. So this is called nitric acid. Okay, nitric acid. So this is called a hydronitric acid. Okay. This is called a hydronitric acid. Make sense? Okay. So this is how we name those acids with the monoatomic ion. And by the way, what is this called? This is called water. Okay, this is not acid. Okay, so this is one of the exception. It has a hydrogen in front, but this is not acid. Okay, so this is water. Okay, we're not calling this as a hydroxylic acid. There's no such thing. Okay, yeah. So this is water. So don't count this. This is not acid. This is one of the exception. All right. So next part. So if the anion is polyatomic ion, then we give its name is pretty straightforward. Okay, you just need to know what kind of anion it is. For example, HNO3. Okay, HNO3, in this case, you just need to go to your common ion sheet to look at what is the name of this anion. Go to take out your common ion sheet and find out what is the name of this NO3. It should have a minus. Okay, so what is the name for the NO3? It's a polyatomic ion. This is called a nitrate. Okay, so you can see this is a hydrogen ion plus a nitrate ion over here. So in this case, how do we, this is called a nitrate. Okay, so the rule in to name the acid is, if you see some of this polyatomic ion ending is at ATE, then you change the ATE to IC, then plus acid. That's it. Okay, that's it. This Ni is ending is ATE, so you replace the ATE to IC acid. So that's it. Okay, so that is why HNO3 is called a nitric acid. Okay, it's called nitric acid. And by the way, I really want you to separate those two. Did you see what is the difference? This guy has only attached with monoatomic ion. So this is, we are adding hydro in front. So hydronitric acid. But this one, they are having the polyatomic ion, so there's no hydro in front. Okay, so instead we just call this nitric acid. You see what's different? This hydronitric acid, this is nitric acid. Make sense? Okay. Okay, so H2SO4. Again, this is, you can see is a hydrogen ion, two of the hydrogen ion, and plus this one of the sulfate ion. Okay, so this is called the sulfate. This is called sulfate. The sulfate is a little bit different because this one you need to add a little bit letters. So we get, still we're going to get rid of the ATE, but we're going to we get rid of ATE and we're going to add IC acid. Okay, but the point is we need to add some of the letters in between the F and I. So we're going to change this called the sulfuric acid. To be honest, I don't know why they have additional one. Sulfur, this is what we have. Then this is called the sulfuric acid. So this is a special one, okay, for the sulfur. And if you see HClO3 or HClO4, okay? So you know, what is the name for the ClO3 minus and the ClO4 minus? You have your own common ion sheet. ClO3 minus, that means the name is called chloric acid. So sorry, this is called chlorate. And this one is called perchlorate. Okay, this is called chlorate, this is called perchlorate. Is there a difference? Well, yes. So again, the rule is the same. The ending is ATE, so you change the ATE to IC acid. That's it. So the first one is called chloric acid. And the second one is called perchloric acid. That's it. You see, it really doesn't matter whether it has a prefix or not. It's just care about the ending. If the ending is ATE, you just replace the ATE. That's it. Okay. Yeah. Are you with me? Okay. But the polyatomic ion sometimes is ending with ATE, but sometimes there's another one, right? It's called ITE, right? So for example, HClO2. This one is a ClO2 minus. This one is called chloride, right? The ending is ITE. It's not ATE. If you see this one is ITE or this one HClO, ClO minus is called a hypochlorite. So different from the ATE. If the ending is ITE, then you're going to change the ITE to OUS. So we're going to replace the ITE to OUS and acid. Okay, so this one is going to call the chlorous acid, and this one is called the hypochlorous acid. Okay, so in general, if you're naming for the acid with the polyatomic ion, you just look at the polyatomic ion's name. If the ending is ITE, you replace the ITE to ic acid. If its ending is ending is ATE, you replace the ATE to the ic acid. If ending is ITE, you replace the ITE to OUS acid. That's it. That's it. Okay, that's it. So this is a naming for the acid. The next part, we're going to talk about the naming for molecular compound. The naming for the molecular compound. So first of all, we talk about the ionic compound. First, we talk about the ionic compound. When we name it, it's just know the name of the cations, name of the anions. You combine them together, you will see the name for the ionic compound, right? But for the molecular compound, is different. Okay, ionic compounds, we balance the ionic compound is because they're charged, right? So we just talk about their name. We know what is the charge for each of the ions, so we know what is the formula. But for the molecular compound, it's different. Molecular compound, they are binding together without a charge. So in general, if you're talking about one of the name of the compounds, you even don't know how many compounds, what is the formula. For example, we all know this, CO and CO2, right? If we base on the name for the ionic compound, and then we should call this carbon and this is oxide. So we just call the carbon oxide, right? But the point is, I mean, there's a lot of different kind of carbon oxide. Could one oxygen could have two oxygen, right? And some of the nitrogen oxide, they also has maybe NO, NO2, N2O, N2O4. So those are all different molecules, okay? And if you look at over there, then you will see, well, in the ionic compound, we always say you need to make the simplistic ratio for a molecule, right? For a compound. But for the molecular compound, we're not going, this is not a rule, okay? Some of the molecule could just has one nitrogen, two oxygen. Some of the molecules have a two nitrogen and four oxygen. Those are two different molecules. So you cannot easily just simplify the molecules, okay? I mean, they give you the different molecules. So this is a molecular compound, okay? Molecular compounds, when you name those compounds, you have to specify how many numbers of those molecules, or how many numbers of those atoms in the molecule. Okay, so that is a very important part. Okay, you have to specify. So that is why when you specify this compound, I mean, usually right now we only talk about the compound with only just with two atoms, or with two atoms. By the way, still remain. Okay, molecular compound is made by non-metal plus non-metal. Okay, so both of those are non-metal. So they, when they attach each other's, is not with the ion. All right, so when we talk about those, we need to specify how do we name the first atom, how do we name the second atom. For the first atom, we just give it a name. Just equal the element's name. And then we're going to plus the prefix if the number of the first atom is more than 1. Okay, so for the first atom, usually if this guy only have 1 atoms, you just need to give its name. For example, this guy only have 1 atom, so you just call carbon. Okay, and this one is also called carbon. But since this guy has a multiple, they have a 2 nitrogen, then you need to add a prefix. For the prefix for 2 is a di. Okay, it's a di. So this is called a dinitrogen. Okay. So when you call this, it's called a dinitrogen. Okay, then if you're talking about second, for a second atom, the name is equal to always add prefix. And then you plus element's name. Then the ending plus IDE ending. Plus the IDE ending. Okay, so this is for the second one. Okay, so first let's talk about what is the prefix. And then we're going to give you some of example about the name of those molecules. The prefix. If 1, then that's a mono. 2, that's a di. 3, that's a tri. 4, that's a no, not hexa. Tera. No, not a tera, tetra. Tetrahedral, tetra. Okay, so 5 is a pentagon, penta. Okay, so 6 is a hexa. 7 is a hepta. 8 is octa. 9 is a nona. 10, that's a deca. Okay, so we only talk about the one from 1 to 10. Okay, we're only talking about from 1 to 10. So do you know where those come from? I'm just asking, I'm not sure. Does it come from the Greek letter or from Latin or from somewhere else? What do you think? Any idea? But usually we use those prefix, right? Very common. We commonly use those prefix, right? Yeah. Okay, so let's just give some of the example. Okay, so that's why CO, that's called a carbon. You see, first elements, if it's more than 1, we add a prefix, but this one only just 1, so just a name for carbon. Second elements, we always add a prefix, even they only have 1, so always add prefix. So this one is called a carbon, and then this is a mono, and then oxide. So this is called a carbon monoxide. Carbon monoxide. CO2, and you know this is called a carbon dioxide. The di means they have a 2. Okay, dioxide. Carbon dioxide. Okay, so but then N2O4. So this one is called the dinitrogen tetroxide. Dinitrogen tetroxide. Okay, yeah. So how about this one? CCl4. Think about this. What this called? Carbon tetrachloride. Okay, carbon. So carbon tetrachloride. Okay, carbon tetrachloride. Okay, so let me see. Okay, how about this? So a lot of the a lot of those molecular compound is pretty weird. They you probably never see this before. Okay, O2ClF, Cl7. So first one, this guy has 2 atoms, so there's a dioxygen. This one dioxygen. 7 is a heptachloride. Okay, dioxygen heptachloride. All right. So generally, when you give us a name, those prefix is telling you how many numbers of the atoms of there. So you can, based on those the prefix, very easily to write down the formulas, right? So the di means 2. Okay, one important thing is a lot of people, for example, if I give you the name like this, some of the students, okay, they made a mistake. They say, oh, dioxygen heptachloride. So dioxygen hypochlorite. Okay, so they're writing the formula like this. Obviously, this is not correct. We never write those numbers in front of elements in a formula. Make sense, right? So we never write like this. So the di, they do talk about we have 2 of oxygen, but where the 2 you're gonna put? You're gonna put the 2 underneath of the oxygen, right? You're gonna put the 7 underneath the chlorine, not in front of that. Does that make sense? Okay. So how about this one? What is this called? So 4 tetra phosphorus deca oxide. Okay, so you just need to specify what is the prefix. If you know how to pronounce those prefix, how to write down those prefix, then you should be able to know how to write the formula. Okay, or how to give it a name for this. Are you clear? Okay, so the prefix here is showing you how many numbers of those atoms over there in the formulas. Okay, yeah. And one very important thing, don't specify, don't simplify those. Okay, don't make this as a P2O5. Those are the different molecules. Okay, those are the different molecules. And very easy mistake is a lot of people, they give it, when they give it a name, they just start to give it a name without seeing what kind of compound it is. Is this an ionic compound? Is this a molecular compound, or this is acid? So please do not give us a name for for an ionic compound, and you put the prefix up there. Okay, so here we have those molecules over there. What is the name? First, you're going to identify, is it an ionic compound or is it a molecular compound? Calcium plus oxygen. Calcium is on the very left side here. So this is a metal. Metal plus non-metal. So this is ionic. So this is called a calcium oxide. Okay, so this is a calcium oxide. This one, nitrogen and oxygen. Nitrogen non-metal, oxygen non-metal. So non-metal plus non-metal. So you have to give its name as a molecular compound. So this is one is called the dinitrogen oxide. How about this one? What is Na? It's a sodium. Sodium is a metal or non-metal? It's a metal. So metal plus non-metal, then this is ionic compound. So that's why this is just called the sodium oxide. And what is this called? Potassium. Potassium is metal or non-metal? It's a metal. So this is called a potassium oxide. And how about this? One carbon, this is carbon, oxygen. So carbon and oxygen, that's all non-metal. So this is molecular. So this one is called a dicarbon dioxide. Okay, you see, only the molecular compounds need add the prefix. Okay, ionic compounds you don't have to. Okay, you don't have to. If you add, you got it wrong. Okay. All right, so let's take a break and then we will talk about the unit 2 content. Okay. Yeah. Okay, so the next part we're going to talk about the content in the unit 2. So first of all, we're going to start with atomic mass for a formula. Okay, atomic mass for a formula. So last time we talked about where to find the average atomic mass in the periodic table for elements, right? We already see that. So the elements like potassium, this is 19, and you see the down there, they have a 39.0983. 39.0983, and this is the average atomic mass for the potassium, which means it talks about this guy, one potassium atom is equal to 39.0983, and the unit is AMU, which is this is atomic mass unit. Atomic mass unit. Okay, so this is for the one elements. But if you have the formula like a potassium oxide, so this is potassium oxide. So now, what is the formula? What is the mass for this molecule? Well, then you just need to see, okay, how many atoms, potassium atoms in the formula, how many oxygen atoms in there, and then you just put them all together, put their average atomic mass for each of this, and then you will get the answer. For example, we have a 2 times of the potassium plus 1 of the oxygen. So in this case, we have a 2 times the mass of the potassium, which is 39.0983, and plus the oxygen. Oxygen is 1 time. This is a 15.9994, and this unit AMU, and this unit also AMU. And then just put this into your formula. 2 times 39.0983 plus 1 times 15.9994, and we got 94.196. 0.196, and this unit is AMU, and this is telling us, okay, the mass or the molecule mass, the formula mass of the potassium oxide is 94.196. That's really just coming from the mass of the potassium atoms and the mass of the oxygen atoms. Okay, so this is how we figure out the mass of each of this. Okay, and this is called a formula mass. This is called a formula mass. Okay, yeah, this is called a formula mass. And some of this mass could be very, very complicated. Okay, for example, we have one of the formula like this. Okay, here we have a dot in between the copper sulfate and the water. So we have one of the formula. This is a whole formula. Okay, this is a formula for one of the compounds. It's not for 2 different compounds. Okay, and we give its name for this kind of stuff with the water, with a dot and plus some of the water out there. We give it a special name. This one is called a hydrate. And this is a part of the information for our lab 20. Okay, so that's why we're talking about this. So this is called a hydrate. And this water over here, it's not the dot here, it's not a modification. It's not the modification. And this is a symbol talking about the water molecules is attaching on the copper 2 sulfate. Okay, it's attaching on the copper 2 sulfate molecules. Okay, so make this this molecule as a crystal. Okay, without the water, they're not going to be a crystal. They will be a powder. Okay, they will be a powder. So this is one called hydrate, and this one without water. You see, if this formula without water, we also give its name. It's called anhydrous. It's called anhydrous. All right, so for this kind of complicated molecules, how do we figure out the mass? Well, generally it's the same thing. You're gonna figure out, okay, what kind of stuff, what kind of elements or what kind of atoms are in those. Well, for this this hydrate, copper 2 sulfate pentahydrate, we have one copper, right? We have one of the copper. We plus one of the sulfur. You see, we have one of the copper and we have one of the sulfur, and the combining 4 of the oxygen. Okay, so this is for the copper sulfate, and then we also has a 5 of the water. So once you count the water, you're gonna say, okay, the 5, it doesn't mean it has only 5 of hydrogen. Okay, they have a 5 of the whole molecules of there. Okay, so last time we talked about we never write the number in front of the elements except we have multiple this kind of the elements. Okay, so the 5 over here is only shows we have a 5 of the water molecules over there. So this is a 5 of water molecule, and what is we have inside of water molecule, we have a 2 of the hydrogen and 1 of the oxygen. You see, so this is how we count the mass. And then what are you going to do? You just need to go to the periodic table and put those mass of each of the elements in there. Then you will figure out the mass of these formulas. Okay, so copper, that's a 63.546. Sulfur, 32.066. Oxygen 4 times 15.9994 plus 5 times 2 times the hydrogen 1.008 plus 1 times 16. 15.9994. Okay, so then you add the stuff all together. 63.546 plus 32.066 plus 4 times 15.9994 plus 5. You're gonna have a parenthesis 2 times 1.008 plus 15.994. And you got the mass of this formula is 249.6866. And this is unit is AMU, okay, atomic mass unit, which means it talks about if we have a 1 copper 2 sulfate pentahydrate, this molecule, we're going to have that much mass, which is anyways AMU. But last time we talked about the AMU unit is very, very small. Okay, generally it doesn't work for the normal daily life. Okay, is compare is probably is 10 to the -19 gram. -19. Okay, which means you're gonna have put 19 zeros in front of a number. Wow, that's really doesn't make sense, right? Yeah. So we're not using the AMU as a unit for the daily life for the lab. Okay, so that is why scientists they introduce one of the other units is called a mole. Okay, they introduce another unit is called a mole. But the mole, again, mole is not the elements that are in the ground. Okay, the mole is a number. This is a really big number. Remember, mole is not a mass unit, it's a number. Okay, mole is a huge number. Okay, huge number. So when we talk about one more or something, it's just talk about a pack of the number of those stuff. Okay, just like we talk about one pair. So once you hear the pair, you know this pair means we have two of this, right? It's a pack of things, but this pack is two. And you know the dozen, we know this is 12, right? So 2 dozen is just 24, right? Mole is the same thing. It's talk about a pack of number, but this number is really huge. Okay, so how the number is called 6.02 times 10 to the 23rd. This is really big. Okay, and we give its name is called the Avogadro's number. Avogadro. Okay, we call this Avogadro's number. So 6.02 times 10 to the 23rd. Well, for this number, how do we determine how this number, to be honest, is an artificial number, which means, okay, this is by definition. If people doing the experiments and figure out what is the number, they talk about how do we got this number. They said, okay, so if we have 12 grams of the carbon 12, okay, so if we weigh 12 grams of the carbon 12, and then the number of those 12 grams of carbon 12 is the number of the Avogadro's number. Okay, so we weigh the 12 grams of the carbon 12. Okay, so this is a mass, right? But how many numbers of this the scientists can, based on their the experiments, they figure out how many number of those carbon 12 atoms in the 12 gram of those. So they will calculate how many numbers of that, and then that much of the number is we call the Avogadro's number, which is 6.02 times 10 to the 23rd. Okay, so they measure 12 grams of the carbon 12 and try to figure out what is the number of those carbon 12s in 12 grams. And then they figure out a number, and this number is Avogadro's number. Okay, and well, definitely, I mean, different experiments they measured differently. So they combine, they collect all the numbers from everywhere for the whole world, and then they make an adjustment to figure out what is the Avogadro's numbers. Okay, what is Avogadro's number? Okay, so the beauty of the mole. Beauty of the Avogadro's number is if we talk about 1 mole of something. Okay, for example, we talk about one single atoms, one single molecule for this the hydrate, copper 2 sulfate pentahydrate is 249.6866 AMU. And if we have 1 mole of this same compound, then we're going to have the mass, which is 249.6866 gram. Okay, so that is the beauty of the Avogadro's number. So generally, you can convert the AMU to the daily life unit. Okay, so 1 mole of the copper 2 sulfate pentahydrate will be just equal to 249 6899. 6866 gram. So this is by definition. 1 mole of something equal to how many grams? Okay, so we generally can convert the AMU to the grams. Okay, so this is what is this is talking about 1 molecule of the copper sulfate pentahydrate is 249.6866 gram, 66 AMU. But if we have 1 mole of these molecules, okay, for example, we have 6.02 times 10 to the 23rd of these molecules aggregated together, and how much is weight? It's gonna weigh 249.6866 gram. Okay, so now we suddenly we got some unit that we recognize, and then the scientists can, based on this, to figure out, I mean, doing their real experiments. Okay, so that is why. And so here we talk about quite a lot, the 1 mole. Okay, what is the, and we know, okay, mole is 6.02 times 10 to the 23rd. But what exactly, can you imagine what is this large number it is? How large this number it is? Well, give you one of the sense, okay? So lollipop, anyone knows probably the size of the lollipop or the mass of the lollipop? Lollipop is pretty small, probably just like 5 grams. That's just a count. It's only probably 5 grams. If we have 1 mole of the lollipop, can you imagine how much weight it can be? I don't want you to give me a number. Just need to think about, okay, what could be the mass? Could it be the mass of elephant? Could it be a mass of a whale? A mass of the battleship? Okay, a mass of the the planet, mass of the star. What do you think? If we have 1 mole of the lollipop, any idea? You guys are so quiet. Okay, yeah, don't have to be shy. Okay, 1 mole of lollipop could be what? What is the mass? Mass of a planet. This could be, okay, yeah. So I roughly make a measurement. So the 1 mole of lollipop is about like 1/10 of the Earth's mass. Okay, yeah, it's about 1/10 of the Earth's mass. So can you imagine how big the number it is? It's a really big number. Okay, yeah. So that's why we're only talking about the atoms. We only talk about molecule, ions. We're not talking about the real world things, right? Because it doesn't make sense. Another sense is, okay, if we have 1 mole of the donut, okay, the thickness of donut is probably this much, okay? 1 mole of the donuts, if you stick together, how long it could be? To the sun. To the sun, that's just a half of that, and come back. Okay, so that's the distance. You go to the sun and come back. And by the way, you probably just to let you know, okay, from the Earth to the sun, the distance between Earth to the sun we call is 1 AU, which is it's called atomic. Wait, AU is one of the units. It's called a universal. Autonomy, right? It's called 1 atomic unit, which means it's the unit, the distance from the Earth to the sun. So generally, it's from go to the sun and come back. It's probably is 1 mole of the length of the donut stacked together. Okay, It's pretty long, pretty big number. Okay, this is a pretty big number. Okay, all right. So this is talking about the 1 mole. Okay, and then people, since we know 1 mole of the things equal to that of the mass, and so we give it a name to another. We introduce another name. It's called the molar mass. The molar mass. Molar mass is talking about 1 mole of the object, the mass of the 1 mole of the object. The mass of 1 mole of the substance. Okay, so now here we know 1 mole of the copper sulfate pentahydrate is 249.686 gram. So that's why we call the molar mass. The molar mass of the copper sulfate pentahydrate is equal to 249.6866, and the unit, okay, the unit is called a gram per mole. Okay, or you can write a gram divided by mole. So this is a unit, a gram per mole. And generally it's called a gram per 1 mole. So we have a 1 mole of this substance is this. Okay, yeah, so this is called a gram per mole. And if you look at, okay, so what is the molar mass? A lot of people write this is a molar mass, so this is a molar mass short. And if you see some of the cases, people also call this a molar weight. Okay, generally it's talking about the same thing. Okay, the molar mass, molar weight is the same thing. Okay, so how about the molar mass of the sodium chloride? Well, then what are you gonna do? You just see, okay, we have 1 sodium and 1 chloride. So you go to the periodic table to look at the molar mass of the sodium and the molar mass of the chloride. The sodium is 22.9898. 22.9898, and this is gram per mole, and plus the chloride, which is 35.453. 35.453 gram per mole. And then you add them together. You got a 58.4428. And this unit is called a gram per mole. Okay, so this is called a gram per mole. All right, so the molar mass. Now we got the molar mass, and generally the molar mass can be a unit between mole and mass, can be a conversion factor between the mole and mass. And this is a very, very, very fundamental concept in chemistry. Okay, yeah, so eventually after this class, I hope you're gonna remember how to figure out, just you don't even have to look at the equations, just suddenly you can figure out, okay, how to convert the mass to the mole, how to convert the mole to mass. This is the thing I hope you're gonna remember. Okay, so mass, that's equal to mole multiply the molar mass. Okay, and mole, that's equal to mass divided by over molar mass. Okay, mole equal to mass over molar mass. Mass equal to mole multiply molar mass. Okay, so this is the two things. And if you're think about the by definition, you can see, okay, molar mass unit is gram per mole, which means the molar mass by definition should be the mass of the something divided by mole of something, then you got molar mass. That makes sense, right? Yeah. Those two are very, very common. So I hope you can remember this. Hope you're gonna remember it. Okay, so one of the example is, okay, since we already got here, okay. So we have a 10.0 gram of the sodium chloride and figure out how many mole of this sodium chloride. How many mole is How many moles of this sodium chloride is it? All right, then what are we gonna do? The mole should be equal to mass. Again, mole should be equal to mass over molar mass, which means that's the mass of the sodium chloride divided by the molar mass of the sodium chloride. So molar mass of sodium chloride, you can find it from the periodic table. Usually the question will not, sometimes the question will give to you the molar mass. If they don't give to you, then you have to figure out on your own. As long as you know the formula, and then you should be able to figure out what is the molar mass of this formula, right? Yeah. So mass of the sodium chloride you have is 10.0 gram, and divided by molar mass of the sodium chloride. And we just figure out the molar mass of sodium chloride is just over here, you see, is 58.4428. And this unit is gram per mole. A lot of times, I strongly recommend you, when you, doesn't matter when you do the calculation, you're gonna combine with a unit, because especially in chemistry and physics, we always, all the numbers has a unit, okay? You're gonna combine a unit with it. And then after the calculation, you will figure out, okay, what is the final unit you can find, okay, based on the calculation. So you see, this 1 gram and this is gram, it canceled. Now the leftover is just a mole. The mole is flipped up. So the final unit you got is just a mole. Mass over molar mass. 10.0 gram divided by 58.4428. And you got a 0.171. Okay, 0.1711. And this is in mole. Again, we're not done because we need to check the sig fig. The question gave us a 3 sig fig for the answer, so we need to keep three sig fig. So keep 1, 2, 3. The answer will be just 0.171 mole. That's it. Okay, yeah. So mole is mass over molar mass. You got a mole. Okay, mass over molar mass. This is a very, very common situation because we like to use a mole to do the calculation in the chemistry lab. But obviously, we cannot measure how many mole of those stuff, right? I mean, we don't have the unit, the instrument that directly measure mole, because mole is a number of those molecules. How can I know how many number of those molecules? We don't know, right? We can only measure the mass of those molecules. So first we decide, okay, we probably need 1 mole or 0.5 moles of those stuff. And then we do some calculation to figure out, okay, how many gram of those stuff we need. And then we go to the balance to measure how many gram of those stuff. And then we know, okay, since we measured how many gram of the stuff, and based on calculation, we know that's going to be how many moles. And this is what we need. So that's why the mole and mass conversion is very, very common and very, very fundamental in chemistry. Okay, so that's why I hope you're going to remember this. Okay. So now go ahead to figure out the 2 calculations. Okay. again. How many moles of copper sulfate pentahydrate is 100.0 gram? Okay, yeah. Okay, the other one is okay, we have two questions. How many moles of copper sulfate, the pentahydrate, is 100 gram? And I have a 0.33 mole of the aluminum hydroxide. How many gram is it? Okay, so please go ahead and work on this. Okay, so let's review it. And again, some people still have the problem to figure out the molar mass of this. Again, the dots over here is not multiplication, which means you cannot use the molar mass of this multiply the molar mass of that. No, this dots means it's an attachment, means addition. Okay, so you're just using the molar mass of copper sulfate plus 5 of the mass of the water. Okay, so this is how you figure out. We already did this in the previous part. We know the molar mass is 249.6866. Is that right? 68. Let me double check. 249.6866. So that is the molar mass gram per mole. This is the molar mass of this. Okay, and to figure out the mole of that, again, the mole will be equal to mass of the copper sulfate pentahydrate divided by the molar mass of it. So we have 100, we have a 100.0 gram of this, and divided by molar mass, which is 249.6866 gram per mole. Okay, and then let's figure out the answer. 100 divided by 249.6866, and we got 0.4. Okay, so we have 0.4005. See, 0.4005. And if you look at the answer, we have a 4 sig fig for this number, so the answer should give us a 4 sig fig. So you do need to keep the number 5. Okay, you cannot just write the 0.4. Okay, because this one they have a 4 sig fig for 100, so you're gonna keep 4 sig fig for the answer. So this is how many moles that we have. For this guy, we got a mole of the aluminum hydroxide. We try to figure out what is the mass. Well, the first you're gonna figure out what is the molar mass of the aluminum hydroxide. So this guy has 1 aluminum plus, you see, this one, it means we have 3 of the hydroxide ions. So you're gonna times 3 times the oxygen plus hydrogen. 1 of the oxygen plus 1 hydrogen. This is how you got molar mass. Aluminum is 26.9815. Plus 3 times oxygen, 15.9994 plus 1.008. Okay, so that's gonna be the hydrogen plus the aluminum, oxygen plus aluminum. 26.9815 plus 3 times parenthesis 15.9994 plus 1.008. So 78.0037. And this unit is in gram per mole because this is a molar mass, so gram per mole. Okay, so we got a molar mass of this and we got a mole of this. So the mass of this aluminum hydroxide is equal to molar mass multiply the mole. Okay, molar mass times mole is equal to mole times molar mass equal to mass. So molar mass 78.007337 gram per mole, and your time, how many mole we have? 0.33 mole. And you can see, okay, mole and this mole is cancelled. So the left unit is in gram. So that's why we can figure out this is in gram. 78.0037 multiplied 0.33. We got the 25.74. Okay. 0.5. No, sorry. 25.74. 25.74. And this is in gram. And then we need to double check, okay, what is a sig fig? This guy has a 2 sig fig. So we should only keep 2 sig fig. Instead of 25.74, we need to keep as a 26. So keep this one, and look at the next one. Next one is 7. So we run it up. So the answer will be 26 gram. Okay, 26 gram. Are you with me? Okay, so this is how we figure out the molar mass. So first, let's just go summary what we learned for today. We talk about the naming for the acid. We talk about naming for the acid. We talk about the name for the molecular compound, and they need to add the prefix. Okay, hopefully you still can remember what is the prefix. Okay, what is the numbers with those prefix? And then we talk about what is the concept of mole, and we talk about what is the mole molecule, a formula mass in AMU, and what is the molar mass. Okay, and the concept of mole. Mole is a very big number. Okay, so if we have a 1 mole of the atoms, which means we have 6.02 times 10 to the 23rd of those atoms aggregate together, and we weigh the mass. And this mass could be something in gram. Okay, yeah. So, and we figure out how to figure out the molar mass of each of the compounds. It's just based on their formulas. And to figure out how many these elements we have, how many that elements we have, you add them together, then you got the molar mass. Okay, yeah. Then we do the calculation between the mass mole and the molar mass. Molar mass is a conversion between mass and mole. Okay, you have a mass equal to mole times molar mass. Mole equal to mass over molar mass. Okay, so this is what we learned for today. All right, so let's pack things and we will go to the lab. Today we're going to work on a fun lab, which we're going to burning something. Okay.